Okay.
Perfect. So welcome everyone. Bileşik Algebra and Number Theory seminars we are going on with Professor Ade Irma Suriajaya Chacha from Kyushu University, Japan. And she will talk about pair correlation of zeros of the Riemann zeta function, zero density and simple zeros. Thank you, Chacha.
Okay, thank you so much for the introduction. By the way, Ilker, so sorry for not asking for permission. Just now I saw, because I'm also the host, I saw a couple of people waiting in the waiting room, so I just let them enter the meeting.
Thank you very much. Thank you.
You're welcome. Okay, so I'm going to start. First of all, I would like to thank Ilker for inviting me to the seminar. It's really an honor to speak here. And I'm going to talk about pair correlation of zeros of the Riemann zeta function, which so a part of that was actually already published this year. So we put it on archive about 1.5 years ago. But then, so after a while, we realized that we could do so much better. So this is still in progress, but we got like the most basic and we think like the most fantastic results. So I'm going to talk about that for today. And this is joint work with my colleagues, Siegfred Baluyot, who just moved to East Carolina University this year, I think. Yes. Dan Goldston from San Jose State University and Caroline Turnage-Butterbaugh from Carleton College. Okay, so well, maybe we don't need this introduction, but I thought we should always start with the right definition. So we will talk about the Riemann zeta function, which is the analytic function defined on the whole complex plane except for the point 1. And it can be written as this Dirichlet series when the real part of S is strictly bigger than 1. And then we have trivial zeros. So I don't talk about functional equation and stuff like that, but just as a corollary, we have trivial zeros at negative even integers, and they are all simple. Now, the thing we are concerned about is the location, the exact location of the other zeros, which are called non-trivial zeros. So all other zeros than this trivial zeros. Now, what we know, let's say more or less immediately, is that in contrast to these trivial zeros, which are all real, all these non-trivial zeros are not real. So not to say purely complex, but they are not on the real line. And they lie only within this critical strip, which is in between 0 and 1. Now, the Riemann hypothesis is when all these non-trivial zeros lie on the straight line a half. Okay, and then now what we're gonna talk about is pair correlation. Pair correlation of these zeros, and not really about pair correlation itself, but its implication on the proportion of zeros being simple and on the critical line. So I'm going to start with that. So as you, let me go back just a little bit. As you've seen before, for these trivial zeros, we know quite easily that they are all simple, but we still don't know if non-trivial zeros are also simple. Now we write the number of zeros up to some given height t, and we only need to count these zeros on the upper half plane because non-trivial zeros of the Riemann zeta function are symmetric with respect to the real line. So when you have some sort of distribution on the upper half plane, you get exactly the same one mirrored to the lower half plane. So it's enough to just look at the upper half plane and we count up to some given height t, and we call that number n of t. And of course, we want to count it with multiplicity. So if we have a double zero, then we count it twice. Now, we know that this number is asymptotic to t over 2 pi log t over 2 pi. Well, you can have a second order term, which is minus t over 2 pi. And well, you can also combine them with that guy over here. But yeah, we will only use the main term, which is t over 2 pi times log t. So that is exactly the asymptotic of this number of zeros up to some given height t. well, we have some error, which we don't care right now. Now, we also want to count zeros, which are exactly on the half line. So of course, we hope that all of them are on the half line. Anyway, now, if we count only those zeros exactly on the half line, then we denote that by n naught. Okay. Now, the Riemann hypothesis, as I said, says that they are the same thing. So if this n of t and n naught of t match for all t, then the Riemann hypothesis is true, and vice versa. I mean, this is just a definition. Okay, and then I need another notation is when I add an index s, not really index, what do I call? So parameter s, not parameter. It will be confusing later to say the parameter for now, but yeah, let me just add some sort of label here s, in addition to this 0 over here, to count the number of zeros which are on the critical line and also simple. So which we mean that the first derivative is not 0. Okay. Then what we want to know is the proportion. So the proportion of zeros lying on the half line, and well, usually we work with asymptotics, and then we take this t to infinity, so we do denote that by c naught, and I mean that constant by c naught, and that is what we call the proportion. And with respect to this critical zeros, which are simple, we call such zeros critical zeros just for convenience. So zeros lying on exactly the half line, we call them critical zeros. And for those which are also simple, then we denote this proportion by the c naught s. Okay, so c, or let's say c0, s. Right. And then, of course, the existence is not trivial in the beginning, but it was proven. So we start with C naught. That was first proven, I think it was by Selberg. Okay. So before Selberg, it was only known that, okay, first of all, there are infinitely many zeros on the half line. And then, well, we can have more than t on the half line. But we recall that the asymptotic is, well, in order of t, it's t log t. So we need something bigger than that. And then yeah, so the first time it's proven that you also get some, you can get something positive with the same asymptotic t log t was actually due to Selberg. But the first time I think this effective number was given was just a few decades later by Levinson in 1974, and that number is at, well, he just said that there is at least a third. So, but actually he proved that it is something bigger than a third. So it's 0.3474, which is like more than 34% of zeros actually lie on the critical line. But at that time, he didn't realize that what he computed is not only the proportion of critical zeros, but also simple zeros. So coincidentally, they are all also simple. And that was proven, or let's say pointed out by Hittbrown about 5 years later. So we get exactly the same proportion for critical zeros, which are simple. And then actually we couldn't get far beyond this, but there were a couple of, let's say, improvements, and I actually tried to list up as complete as possible. I think the first time it happened was in 1983 due to Connery. We just went up a little bit beyond 36, but now this is the first time that you don't get exactly the same proportion for both critical zeros and critical zeros which are simple. So when you restrict the zeros to be simple, actually the the proportion goes down a little bit, but it still improves the result of Levinson and Hittbrown. So you see that the decimals here get slightly bigger. But for simple critical zeros, they are still below. They were still below 35%. And then Anderson quite soon proved the combination of zeros being critical and simple to be over 35%. And the greatest breakthrough, which I think I should say even until now, was by Conry in 1989, where he could prove that there are more than 40% of zeros lying exactly on the half line and and which are simple. Okay. Then right. So now I'm going to just introduce. I'm not very sure, but probably there were also not quite any other improvements beyond this, except for these two. So quite long later, by Humbui, again Conry and Matt Young in 2011, that for critical zeros we could finally hit 41%. But for those which are simple, we still couldn't get there, but we improved a little bit from the previous result of Conry. And then just recently, Kyle Pratt, Nicole Robles, Alexander Zaharescu, and okay, sorry, I forgot the first name of Zeindler. Sorry. Okay. They proved that we can improve this a little bit, but actually you cannot really quite get the percentage going up one more integer. So for critical zeros, we still go only a little bit further than 41.0% to 41.7%. And then for the one with simple zeros, it's still not quite to 41%. Now, we want to first focus only on simple zeros. So if we recap what we had just now, now if we combine that proportion of zeros which are also which are on the half line and also simple, we had all these numbers, and you see that we haven't gone far beyond what Levinson did in the first place. But okay, so now if we give up on this proportion of zeros being critical, let's just look at simple zeros. Now I define one more notation, that is NS. So now I only count zeros which are simple. And then I denote this proportion, this asymptotic proportion, by CS. Unfortunately, so far until before our paper, we only had results on RH, I believe. So how did that work? So what Montgomery used, so the original idea came from Montgomery, and we actually also adopt this idea. So I'm going to try to be a little bit more detailed in this explanation. So he defined this F function, which I will call F of alpha, which is in some sense detecting or like looking into pair correlation of two different zeros, or let's say not, I shouldn't say different because they may not be different. So of any pairs of two zeros. And so actually the original definition, which I will also show later, is not quite in this form, but when we count zeros, we actually want to normalize that. And then, so it comes in this form, and we want to normalize that with respect to the asymptotic number of zeros. And therefore we divide it by this t over 2 pi log t. Now, there's a function w here, and this w is just a weight function, which is 4 plus u squared. 4 over 4 plus u squared. And then when Montgomery first defined this function, he showed that we have an asymptotic formula for this function with, I think, a less exact error term at that time, but it was improved later by Montgomery himself and then Goldston in 1987. And I think the most precise form that is sufficient for our use is when you get the asymptotic with an error big O of square root of log t, 1 over square root of log t. here, and also multiplying to the main term. And what's important here is that this holds uniformly for all alpha in between 0 and 1, including the endpoints. But if you recall from Montgomery's paper, he did not prove up to 1, but well, then you can see easily that actually his proof worked up to 1. And this was all covered in this paper.
Just sorry for interrupting. Can you please admit the waiting list?
Oh, yes.
Sorry for. Thank you.
Sorry. Okay.
Thank you.
I just did. Okay. And then, okay, where was I? Yes, this one. And there's just one remark. So if you're familiar with Goldston and Montgomery's paper, you will see that there was an extra term in this error. So actually, they wrote an error which is worse than this one, but actually it was superfluous. So you don't need that term, and you can just go with this asymptotic formula. And this is written in our paper, which was already published, and also the ones coming out. Anyway, now Montgomery did this, but only upon assuming RH. That's why when he defined this pair correlation, he only looked at zeros on the same vertical line. And we are interested on the zeros being on the half line because we expect that they are all on this half line. So that's how he took all these zeros. And he assumed RH to get this asymptotic formula. Then using this, it's not hard to show that at least 2/3 of the zeros are simple. So we get 2/3 proportion of simple zeros under RH. And you see this is like more than 66% compared to the previous unconditional results we went so far beyond. And if you assume some additional conditions, then you can actually also get almost all zeros are simple, but I won't talk about that now. Okay, so anyhow, going back to this Montgomery's result, you can improve on this a little bit. So if you optimize the kernel that he used, I will talk about that in very much detail in the proof later. Then you can go a little bit beyond 67%. So, well, yeah, we're happy that we improve on that. And Cheer and Goldston a little bit later showed that you can improve this further, but probably this is the most optimal number you can get using this method. So you still cannot go beyond 68%, but I don't think we can do that with this method. But if we do some extra effort, so what I mean by extra effort is that you still stick to Montgomery's idea, but you don't only use that idea, you combine that. If I remember correctly, there's additional information on the distribution of primes. Okay, so if you use that, and especially for example in Goldston, Gonek, and Osluk and Snyder, they assume generalized Riemann hypothesis. That is the Riemann hypothesis for Dirichlet functions. It's because they use the distribution of primes in arithmetic progressions. So if you combine that, you can improve on this proportion a little bit better. And in the recent result by Chirag, Gonsalves, and Delat, they could improve that even further, but still not going up to 68%. And this still relies on Montgomery's idea, but you need some extra, let's say, information. And especially what Chirag, Gonsalves, and Delat did is that they use some sort of linear programming to completely optimize the kernel. And this is like so far what we get. Okay, now we can actually go a little bit further, but we need to use completely different methods. So not using this Montgomery's pair correlation idea, but I would say moments method. So you compute the moments of this Riemann zeta function to get better proportion. And with that, you can go beyond 70%, but still, I think this is the best result we have. So the original idea, I think, started from Conry, Ghosh, and Gonek in 1998, and Hungbui and Hit Brown improved that with the same proportion, but by removing this extra condition. So assuming only the Riemann hypothesis, you can get the same proportion. Now, yes, so the reason why this Lindelöf hypothesis, and it's generalized Lindelöf hypothesis, because if I remember correctly, they also use this so distribution of values of L functions. So not only the Riemann zeta function itself, so it's combining Riemann zeta function and Dirichlet functions. That's why you have to generalize also the Lindelöf hypothesis, which talks about the size of L functions on the half line. Right. Now, I want to go back to Montgomery's idea because that's what we used. So the beginning of this result is because we were working on another paper which used Montgomery's theorem. What I called by Montgomery's theorem is this asymptotic formula for Montgomery's F function. But then when you extend that, you don't extend that as what Montgomery conjectured, which is known like Montgomery's conjecture, and you also know Montgomery's pair correlation conjecture. But there's another conjecture as another extreme side to that conjecture, and we were working on that. But then we thought, I think we can remove the Riemann hypothesis in this Montgomery theorem, and let's see what we can do beyond. But then we got so excited, so we've been we haven't been extending this asymptotic formula to like larger region, just like this Montgomery's conjecture and all this stuff. But we're still stick to this because we found lots of interesting things can still be done. But so in the original paper, we really just generalized what Montgomery had by replacing the summation of zeros, not okay, so what do I want to say? So by replacing the summation over zeros to not only zeros on the same vertical line, but just any pairs of zeros. So what you want to do is you replace gamma in Montgomery's theorem, because gamma denotes the imaginary part of the zeros. We replace that by rho, just zeros itself. Okay, but then because we don't want to have like I over here, we change the weight to minus here, but it really doesn't matter. So it will so if you want to still stick with Montgomery's weight function, then you have plus here, then instead of rho minus rho prime here, you just put minus I. No, it will still match. We just don't like how it looks, so we adjusted that a little bit. And then another thing we adjusted is now we count the zeros not from 0 to some height t, but in between t and 2t. But in the previous paper, actually, we did it for 0 to t. Now we change it for some good reasons, which probably will be clear as I go through the proof. But in any case, even though you shift it this way, you can still convert it to the summation over zeros in up in between 0 and t. So it really doesn't matter. Sometimes you might need some slight modifications, but you can still convert it. And also, another thing I want to point out, I already said that if the Riemann hypothesis is true, of course, you can always go back to Montgomery's original F. So this all these slight modifications do not change the essentiality of Montgomery's idea. Now, this F alpha, Montgomery's F alpha actually is defined to be, you take x to be t to the alpha here, okay, and then t remains the same because this t just denotes the height. So zeros in some certain region, okay? And then, of course, if you want to count zeros, then you usually want to normalize it. So what you do is you divide it by the number of zeros, right? Now, as in the case of Montgomery, it was the summation over zeros in between 0 and t. That's why you only need to divide by its asymptotic, and that was t over 2 pi log t. But now, because we are picking zeros in between t and 2t, now you have the difference between zeros up to height 2t and zeros up to height t. So that, I mean, that really doesn't change much of anything. Now, the first result is, I mentioned it here in 2 years because we already had this result, but with a slightly different definition of f, because we didn't shift it to t, but essentially the result still remains the same. So I keep it with 2 years, so from the previous paper and the upcoming papers. Now, we still have basically the same asymptotic, but I want to be simple here because we, at least for this talk, we don't really need it to be 1 over square root of log t. So I just write it as small little of 1, but that's all. Basically, the what it says is exactly the same as what Montgomery said. Sorry, I forgot to change this to f, Metcal f. So calligraphed f, sorry. Because I mean, we are working with this Metcal f, so I have to change this, sorry. So basically, we still have the same statement. This function is real, even and non-negative, and it satisfies this asymptotic formula as t goes to infinity, and this holds uniformly for alpha in between 0 and 1. Because this is even, it works for alpha in between -1, 1. Okay. Now, okay, so the exciting part. If we use this let's say unconditionally, so you notice the only thing that is different is that we removed RH. Now there is no more condition in this theorem. This is a completely unconditional Montgomery theorem. So we're happy. But to be honest, I mean, probably most of you who worked in this direction already noticed the proof of Montgomery itself does not really rely on RH. So it was not hard to remove RH at all. It's just that nobody wrote that in a paper. But the problem is that, okay, so we did that, we are happy. If we don't have any applications, then should we write that or not? And then we thought, okay, because Montgomery worked on the proportion of simple zeros, let's also do that. Now, the problem is that we cannot do this completely unconditionally. So the range of zeros, so you have this, well, Korobov-Vinograd zero-free region, and then you can also dump in zero density estimates, but still it's not enough to confine zeros to a smaller region and show that the rest of the region does not contribute much. So unfortunately, we have to assume something, and it looks a little bit strong, but it's really so much weaker than the Riemann hypothesis. So the Riemann hypothesis says that all these zeros lie exactly on the half line. Now we allow a certain width, okay? But now, okay, we don't want this gamma to go from 0 to t, because then when t goes to infinity, it will, this range will just go to a half, and that will just be the Riemann hypothesis. So that is like ridiculous. Now, the thing is that if you count only up to t of 3/8, then actually it doesn't contribute much to whatever we do. And therefore, it's enough to just assume that whenever you pick a t, okay, so you do this pair correlation of zeros, you pick a t, right? And then with respect to that t, you take a box. So from t to the 3/8 up to t, and with width 1/2 log t with the same t, okay, around the half line. Now you allow so only in within this height, you assume that you don't have any other zeros. Okay, so you assume that all the non-trivial zeros will lie within this box, within this height. Okay, but when gamma is less than t to the 3/8, we really don't care. So you can have zeros close to 1 and we don't care. Okay, now what we got before is that unfortunately we cannot get 2/3. We really thought we could, but we couldn't. And I will show you the reason why. We only could get to 61.7% of zeros being simple. So assuming that you only have zeros within this box, then you get 61.7%. And then you can replace, if you don't like this assumption, you can replace this with a density condition. Okay, so this is just saying that you have a slightly stronger zero density estimate, but you don't really need to go to 1 because there was already a result by Jean Bourgat that when the real part is bigger than 25/32, you already have this strong density estimate, and we want that to hold not up to the critical line because we can allow this distance 1/2 log t. So we only assume that this holds up to there. But okay, this still looks a little bit strong, but this is so much weaker than RH, right? And you can still get the same proportion. So basically, I'm just saying that I can replace this assumption with this one. But okay, we were not happy with this, but there was nothing we can do because it was the best we could get. Then we noticed we did something stupid. We could do so much better, but it was so hard to see, and it took us over a year to realize that, and I'm going to explain that today. So now, okay, what we do is, so the original idea is that now we want to allow some this box to move a little bit. Okay, so in the previous one, you see it was 1/2 log t, and then I want to change this width. Okay, so not to say that I certainly will take a box bigger or smaller, okay, but let's just allow there's allow a parameter b here, okay, and now since we use metcal f, okay, what we use right now is metcal f, right, and then we are only picking zeros in between height t and 2t. So now we only need to assume zeros being within this range for only that height. So now I denote that set, okay, just this region, this box region by b now. Okay, so this is a box of width b/2 log t around okay, so it's twice of that. So to the right it's b/2 log t, to the left also b/2 log t around the critical line in between height t and 2t. Now, if you assume that all these zeros are in this box, okay, all zeros in between this height t and 2t are in this box. If, okay, this is a little bit sad because then you have to take the width getting close to 0 as t goes to infinity. But if we do this, then we can get 2/3 proportion, just like Montgomery had. And we also found, whoa, we missed this part in the proof. Then if we use that, we don't only get proportion of simple zeros, but we also get proportion of critical zeros. So now we come back to proportion of critical zeros because we are not assuming RH, right? We don't know whether they are on or not on the critical line. But of course, I mean, this is still a strong assumption on the location of zeros. But anyhow, we can also get 2/3 proportion of critical zeros. This is nice. And then we want to combine this, but unfortunately, like with easy methods, you cannot quite get that far. So with just our simple ideas, then you can only get a third. It's basically like half of this, like the overlap of this. Basically, that was the idea. Now, well, you might not be very happy with this. I mean, well, I agree. This is a little bit, wow, looks like almost RH, but you can actually, sorry, I wrote it as the same assumption, but what I say by assumption is only this one, okay? And then I take a particular b, so I fix b. I'm not taking b close to 0, okay? So I fix b, it's actually 0.001. Then with a very good kernel, we can improve this proportion to this one. And if you notice this looks like the proportion that Montgomery and Taylor had. And actually that was our idea. And this one coming here is really, as I said, was just the overlap of this. So it's like about half of this one. Okay, anyhow, now I'm gonna show you how we did that. Okay, so so the first thing we do is we just do some Fourier transformation, just like what Montgomery did. So we assume we have a kernel, and then we take its Fourier transform. Now, then this okay, what okay, I'm gonna change what I say later, but wait a moment. I forgot if here, but anyhow, you can regard either R or R hat is the kernel because we always take a pair of that. Okay, so now this Fourier transform of the R you took will come in here, and then if you multiply that by with this weight function that we had in the f function, and you sum over zeros as in the f function, then you can actually compute that, and that is, well, asymptotic to t over 2 pi log t multiplied by the value of r at 0. So now you already notice if we don't take the same kernel as Montgomery, then the result degrades. So that is the secret behind the 61.7%. Anyhow, I wrote this for zeros in between 0 and t because I'm only citing the lemma from our previous paper. But if you change this range to t in between t and 2t, you still get the same asymptotic. I mean, I've simplified what I wrote here a little bit, but basically this is what we said even in the upcoming preprints. Okay, now I'm gonna choose a kernel. So the idea is, because we don't only take zeros on the same straight line, we need the kernel that also works for complex numbers. So the idea comes from Zhang's paper when he looked at large values of the Riemann zeta function in the 1990s. So he took a kernel with respect to this sphere kernel. Okay, so the sphere kernel just looks like this triangle supported in -1, 1. And the peak is really exactly at the origins, at the origin, sorry, at alpha equals 0. Now the Fourier transform of that is this pi t over sine pi t square. Okay, now what he used is, now he tweaked it with a hyperbolic cosine. Okay, now our new idea is that, so in Zhang's original idea, we didn't have B here, and we had that in our previous paper. That's why we couldn't get the 2/3 proportion. Now, if we have this B, we can do better. Okay, now I want to change the notation here. You notice here, I took the Fourier kernel and then I computed the Fourier transform, but now I changed the location of the hat because it really doesn't matter. You take a Fourier transform pair, you have a function and then you have its Fourier transform. You can also call the Fourier transform the Fourier transform of the Fourier transform the original function. So so it doesn't matter. Now we switch it just because it was easier to write in like our method, so we just like it better. So now I call the tweaked kernel k hat right now. Now I take its Fourier transform and I call it k. So now we take this pair kb and kb hat. B comes from this parameter b. Now even with this extra b that Zhang didn't have in his original paper, we still have the same. So I mean, this kb still satisfies the same properties as what Zhang proved, and this is really nice. First of all, it has positivity. So if you take the real part for complex numbers x plus iy, okay, as long as your y is not too big, then it's positive. And this is what we need. This really is what we need, because the idea beyond Montgomery's proof is using positivity of the kernel. But what he had was just the Fourier kernel, which is real, and everything just worked like automatically. But now when you take zeros not on the same line, you have complex numbers, and that's why we need to tweak this kernel. Now next, the second condition we need is a fast decay of the kernel. Now only these two properties, but this is really nice enough. Okay, now okay, so going to the main idea, Now, if we denote the multiplicity of a non-trivial zero row, okay, by m row. Now, if I sum over, so in the, okay, so if I go back to my lemma and then I take here instead as this R had my KB, okay, I take my KB there, and then sorry, I forgot to put B here. I was like correcting the slides from an earlier slide. Yeah, some of them I did not get corrected, sorry. So this KB, okay, and then I want to take its real part. But now, so I originally have over all pairs of zeros in between t and 2t, but now I take only the diagonal terms. So what I mean by diagonal terms are zeros which are the same, right? When rho and rho prime are the same. But what happened is that when you have the same guy there, then it's just zero over here. But then because you need to count, I mean, well, this is originally this is a double sum, right? Because you run over row and row dash. So you get the multiplicity of zero multiplied inside the sum. Now, you might have noticed that I lost my weight here, but actually we can show that we can remove the weight. So that will come back, I think, pretty much later. But now we just take this summation without the weight. Okay, we take the real part. And then by using our lemma, so from this lemma, sorry, sorry, it's not a good order because I want to use this lemma, so I still have to show that you can remove the weight first. Yeah, it's not in a good order, but yeah, you can remove the weight, and then from that lemma you can no, sorry, I again confused myself. No, right now you don't need the lemma yet. Yes, you don't need the lemma yet because here you just use the definition of KB. So it's just this one. And then, well, I just write it because I mean, these functions are simple enough and it's just nicer to see. Now, because I'm letting b going to 0 as t goes to infinity, then what happened is that this integral over here goes to 1 over 2 pi. So asymptotically, this is 1 over 2 pi. And therefore, my summation, okay, my summation with my kernel here and the multiplicity of zeros over, and this is only, this is not the double sum, this is only sum over zeros in between t and 2t, not two zeros, okay, not pairs of zeros. Okay, goes to the summation of this guy with 1 over 2 pi here. Okay, now there's another term I want to take out. What I did just now was I was taking diagonal terms when the zeros are the same. Now we notice that there are also symmetric diagonal terms. So zeros which are not the same, but when they are flipped with respect to the half line. So now I'm gonna take this one which are not on the half line. And then if I compute this kernel, I have this integral and I do the same thing. So I let b go to infinity when t goes to I let b go to 0 as t goes to infinity, and again this goes to 1 over 2 pi asymptotically. Now I'm gonna put this all together. So finally, the positivity of our kernel works. So you saw the second condition of the kernel that actually was used when we removed the weight. So yeah, sorry, I should have put that in the slides. But now we don't have to worry about that. What we use right now is just the positivity of the kernel. So because when I take this real part and because I'm assuming that all my zeros are within the box, then it satisfies the first condition. So I say that this imaginary part should not be too big, okay? But the imaginary part in our summation is then the real part of zeros. That's why we have to restrict the location of real parts of the zeros. that was the reason why we had that assumption, that box assumption. Okay, but then we guarantee that our kernels, the real part of our kernels are positive. So if you take only a part of that sum, that will be less than the whole sum. And then, of course, the original sum is a sum over pairs of zeros. So this is a double sum. Okay, now, yeah, sorry, I just mentioned here that that I removed the weight because this is the first time we need to use the lemma. So now we want to use the lemma here. Okay. Yeah. So and then we can compute this one. So this one is equal to the one with weight n when we remove the lemma, when we remove the weight, and that one is small. So this is essentially exactly the one with the weight, and from the lemma you get the exact function that describes the summation. Okay, so now I'm just gonna put this all together. So I have the diagonal terms, the symmetric diagonal terms, and this is less than what I had here, and then I just compute this. And when I compute that and I take t goes to infinity, then that b goes to 0, right? So this becomes a much simpler integral, and actually this becomes 4/3 times the asymptotic number of zeros. Okay. Sorry. So yeah. So that one was not 4/3. It was, wait a moment. So you combine this, you get 1/pi, and then from here you get, I think it was 2/3. Yes, 2/3 plus 2/3, so it's 4/3 pi, and then you remove the pi. So now you get these two summation being smaller, or at most this 4/3 asymptotically times this t/2 pi log t. Now the first one I want to do is I want to count just simple zeros. So I follow Montgomery. So the idea is that now I only take the first sum. Okay, so this plus this is less than this guy, but now I'm only gonna take this one. Okay, but this is still less than this one, right? This is still less than that one. And then the proportion of simple zeros can be described as the number of simple zeros is, you can bound it below by the number of 2 minus the multiplicity of zeros. And that is if you used yes, if you use this number, then it's 2 minus, so this is at least 2 minus 4/3, and that's why you get 2/3 times the asymptotic number of zeros. Then this implies if you take the limit infimum as t goes to infinity, then that is 2/3. So this is our simple zero proportion. And then we do the same for critical zeros. So you have seen all the ideas just now. We do almost the same thing, but this time I want to take what did I do? I want to take the second summation. Okay, but we first notice that we should note that the summation over just all zeros of the multiplicity of these zeros, it is of course at least the summation just of all zeros, because the multiplicity is at least 1, right? And this is just the number of zeros in between t and 2t, so you just have the asymptotic formula for the number of zeros. Now we want to make use of that, and then from our computation just now, I take this one, this is less than this guy, right? Then the 4/3, this is now right, so this is less than wait a moment, I think I had a typo here. Anyhow, wait a moment. Yes, I think I had a typo because this was no. No. It's just because I skipped one step here. So because this is summing over all, and this is summing over only the ones which are not on the half line, then this one is bounded by when you sum overall, and then you remove the ones which are exactly on the half line, and right, and then therefore this summation over zeros which are not on the half line gives you 1/3. And now I want to take only the, wait a moment, what did I say? I skipped one line here and now I confused myself. Yeah, so sorry. So I was not subtracting by the number of zeros exactly on the half line, because that's what I'm going to do just right now. So this is only rewriting this one from the original summation, and then some extra terms, and then you get sorry, I was being stupid. Let me go back. So what I did just now was that I want to say that this is at least, well, this guy, so this guy minus this guy, right? This is not at least, at most. This is at most that guy on the right hand side minus the other sum, and then that other sum is bounded below by this one, and therefore this is bounded above by this minus this one, and that is 1/10. Oh, sorry. And then now I want to count only the ones which are on the half line, and therefore that is the summation over all the zeros minus the ones which are not on the half line, and therefore that is this 1 minus 1/3, and therefore we get at least 2/3, and this gives the 2/3 proportion for critical zeros. Now I'm really almost done. So now when I combine this, so if I want to count zeros which are on the half line and simple, then I just want to subtract the ones which are not on the half line from all the simple zeros we have. Okay, so this summation over, so the number of simple zeros, as we did just now, we have seen that it is at least 2/3 of the whole number of zeros, and this y over here is bounded above by the summation with the multiplicity of zeros for zeros which are not on the half line. And so if I take minus, then it bounces this whole thing from below. And then right, and therefore there you also got 1/3, right? So this one we had that it's bounded above by 1/3, so the minus of that is bounded below by 1/3, and then 2/3 minus 1/3 gives you 1/3, and therefore this simple critical zeros we can only get up to 1/3 proportion. Now you can generalize the kernel for this only to explain how we can get the improvement in the second theorem. You can generalize the kernel further. You still do the same thing. So instead of this, the integral we had just now, we just we keep the kernel, okay, here, and we still have the hyperbolic cosine. Just now in our case it was 1 minus alpha, but now we just replace that with a kernel. Now what we want to use is exactly Montgomery-Taylor kernel, and that's how we can improve the proportion. But this time we don't take b going to 0, we just take a fixed b, 0.001, and we actually will show a table how the result degrades as b goes bigger. Now this is my final slides. I have told you before, the reason why in the previous result we couldn't get 2/3 proportion, it's because we took b equals 1. So you can get better results, but of course you have stronger assumption. Basically you only allow zeros in a very, very small box, like thin box. Now we can in this result also, we can replace the assumption of dislocation of zeros by a strong density hypothesis that still works the same, but I didn't want to explain that just now. And then we can weaken the assumption further by copying the boxes finitely many times. This is what I really wanted to do from like last year. And finally, we could do that. But if we have finitely many boxes, not only one box, you have a finite number of boxes, then you need to assume the zero density hypothesis. But, well, actually, this idea also come originally from Maynard and Pratt's recent work. They published that, no, sorry, they put it on arXiv, I think in 2022. And then they replaced that with a newer version last year. And I think I still haven't found their published version, so I write it as 2024 plus. But anyhow, they had this finite vertical lines assumption and stuff like that. We were inspired by that. We tried to copy our boxes. So our box to boxes. And then with their result, we can show that the zero density hypothesis holds. Therefore, then if we squeeze our boxes to lines, then we have that. So we just need to assume that there are finitely many, that zeros only lie on finitely many lines, then we have our results the same way. And okay, thank you very much for your attention. That's all I will say.
So thank you very much, Chacha, for this nice talk. And first of all, I would like to say a really special thank you because it is almost midnight in Fukuoka, but you are still alive at 11 p.m. I guess.
Luckily.
Yes, I have to admit that I missed some parts because of my not ending duty today, but I perfectly listened last 30 minutes. But we have record link, and if you don't mind, we want to put it in YouTube in our channel, seminar channel. It will be the first video, if you also agree about this.
I see. Yeah, sure. It's okay. Yeah, I did say something stupid a little bit in the middle, but I guess that's okay.
No, I think it's fine, but we can edit it if you like. So thank you very much for this nice talk. It was really nice. Is there any question or remarks? Professor Yıldırım, please.
My question is this.
Yes.
Suppose you assume a little, maybe not a little, but stronger hypothesis, like instead of b over log t, you take, let's say, constant over log t times log t in the denominator. Then what do you get? Is that method generalizable to that?
We thought about that. Well, what you meant is you multiply this by log t.
No, a stronger assumption that you also have a log t in the denominator, let's say. And do you get almost all zeros simple or something?
I see. Yes, we haven't thought about that. Thank you very much for your remark. Yeah. Yeah, we actually
could be log t squared perhaps too. I don't know, but just a little strong. It seems a little, but maybe it's a huge assumption also. But like change the order of magnitude somewhat. Put a log here or log square and see if the method. I don't know if your method is applicable to that assumption.
Yeah, actually, you are being very sharp because we are also preparing like another paper to prove that almost all zeros are simple. So we did see that we can go just a little bit further beyond this, and we haven't checked whether we just need an extra log or we need to square this as you said, but basically we had more or less the same idea. So you were being very sharp about that.
Just a guess, you know. Yeah.
Thank you. Any more questions or remarks? If not, thanks to the speaker again. Thank you very much, Checha.
You're welcome. Thank you very much for.
And this was it was our pleasure. This was the last seminar of 2024, and we will start with the new year with Professor Cem Yalçın Yıldırım next month. I think it was around 12th of January or something like that.
Will also be a talk on pair correlation.
It will be like a continuation talk. It's very nice. It's like a seminar series.
Continuation, but let's say parallel or something like that.
Well, in terms of seminar, it's very nice. Thank you very much.
Yeah.
So I wish
I
you.
told Ilker that it will be nice if you can have the time like today so that I can also attend.
Yeah, we will. Yeah, of course, we will consider the time difference between Turkey and Japan, and I will also ask for Professor Yıldırım if it is okay for him, and let's see. Hopefully it will work, I guess. So I wish you a new year, happy new year for all group members, and let's hope that 2025 will bring us peace and good, happy days. Happy New Year to all.
Yeah, Happy New Year. Thank you.
And Chacha, let's hope that we will meet in Kyushu next year in Sakura
yes,
time.
that's right. That's right. You're coming.
I think it will be like this. Let's keep fingers crossed. So see you in next seminar. And good night, good evening, good days.
Yeah, thank you. Thank you, everyone.
Bye-bye.
Have a good day.
You too.
Bye-bye. Oh, I have to stop the
Yes.
recording.
Yes.
I